And we're back. So we're here again. This is matrix analysis. This is actually our last topic for the semester. We're analyzing frames now, so hang in there. I'd just like to discuss over the derivation for the stiffness matrix to be used for frame analysis. So the procedure is pretty much the same with beam analysis. It's just that for frames, we need now to take into account the actual forces. So what you see here is the actual stiffness that we derived from truss members, and here below is the flexural stiffness that we use for beam analysis. So if you want to remember or recall how we derived these, you can go over the previous slides. All of them involve introducing a unit deformation along the designated freedom and then listing down the stiffnesses corresponding to those deformations. So now instead of two freedoms, vertical and rotational per node, we now have three degrees of freedom for each joint or node. We have actual in this case, shear, and rotation. But it's basically just X, Y, and R or rotation. Okay, so the procedure for the analysis is pretty much the same. You start with your joint coordinate table, followed by your member incidence, destination table, and then the member properties. From there, you now generate your local member stiffness matrix. Local member stiffness matrix. So how do you do that? It's just a matter of arranging your stiffnesses together. So remember, the sequence for our freedoms would be horizontal, vertical, and rotation for the near end, and then horizontal, vertical, and rotation for the far end. So in terms of the degrees freedom, that's 1, 2, 3, 4, 5, 6. As you see here, you have the actual stiffness matrix, which has a destination of 1, 4, 1, 4, and then your flexural member stiffness of 2, 3, 5, 6, 2, 3, 5, 6. So it's just a matter of arranging these two matrices, combining them into a 6 by 6 matrix. So I'll show you that now. Then you get something like this. So you can see here, the first column corresponds to the freedom along freedom 1. Fourth column, stiffness along freedom 4. Then 2, 3, 5, 6 correspondingly. Now, there are values here that are 0 because initially they were not involved in the matrices that we derived for beams and for trusses. So I'd like to go back and do that, show you that one more time. Okay, it's just a matter of combining them in this manner. Okay, now it's pretty straightforward. Nothing new. We're not introducing anything new. It's just that we're using a larger matrix now. It's 6 by 6. So not much to memorize. Okay, but I do want you to take note that these are local member stiffness, which means we still need to transform this into a global member stiffness. To do that, we need to set up your transformation matrix, and to do so, we take a look at this example. Consider small q and x prime as your local force. You need to get its components along the vertical and horizontal. So those are your global y-axis and global x-axis. Now you see here, it's just a matter of using these angles and getting its component, so that's cosine. I also want you to notice that for this author, the derivation that he uses accounts for theta x and theta y. But for our class, we just use theta x, right? Note that These value of cosine theta y is same as sine theta x. Okay, so once you see cosine theta y here, you can just switch that with sine theta x. Alright, so you can get now capital Q and X and capital Q and Y. These are the global member forces for the near end. So N stands for near end. Notice also that we have here capital Q and Z equal to small q and Z prime. This accounts for the rotation or the moment at the joint. So moments don't need to be resolved, so it's just a direct 1:1 value. On the other hand, if you have another force here, small q and y prime, which acts perpendicular to the member, as compared with small q and x prime, it's along the member. You also need to resolve small q and y prime. Okay, so you get its components, get these values. All right, so we're done with the near end. Now you do the same for the far end, although I'm not showing it here, but you'll end up with similar expressions as these at the bottom. Okay, so you have all of these expressions. Obviously, they're just related, or we're just relating the global member forces, capital Q values, and the local member forces, small q values. And the relationship is just a function of the angle, theta x. So if you set up in these into a matrix, you get this. Now I know the slide that I uploaded indicates PML equals H times PMG, but I did mention that capital Q stands for the global member forces and small q stands for the local member forces. So I want you to switch that. This should be PMG, so that's a typographical error, and this should be PML. Okay? Now here you see the transformation matrix. So you just multiply PML with the transformation matrix, then you get the global member forces. Again, this is not that new to you. You've seen this before, although we've been using the simplified version. Okay, so to memorize this, it's just cosine of theta, sine theta, the rest would be 0. This is negative sine theta, this is cosine theta. Now this would be 1. So this 3 by 3 partial matrix would be the same as this one at the bottom. Okay? Then the rest would be zeros. Pretty easy, right? Now you just need those two matrices and then the rest would be the rest of the steps would be the same. So I'm stopping here because I'd like to cut the videos into smaller chunks. So we'll be solving example number 1. This was already solved. The answers are in the slides uploaded previously. But the approach there is kind of different from what we do in class. So what I want you to do is to try this on your own, and then if you do encounter a stump somewhere along the way, I am uploading, the solution video for this one in the next video lecture. Okay, so that would be all for this video. Thank you and stay healthy.